Hello, sixth grade. Here they are, your video review notes to help you as you review for the plate tectonics quiz coming up. All right, I'll do is I'll talk through these notes pretty quickly. These are the same notes you've seen before, but I'll talk through them to remind you of the ideas that they represent and to help you if you need to retake any notes if anything was missing. All right, so we first jumped into these questions about plate tectonics. One of them was the idea that our Earth is geologically active and that other planets like Mars are geologically dead. And these are sort of the questions we have to help us to begin to think about these ideas of plate tectonics. All right, so as we jump in here, first big idea is that continents are drifting. It's this theory that the continents are drifting around and that they once all were together in this supercontinent called Pangaea. But what was this evidence that the continents were drifting? Why did this idea come about? And it was Alfred Wegener who put a couple different pieces of evidence together, and these were the four. The first is that the continents fit together like puzzle pieces. If you look at this picture here, you can see that the side of Africa here and this side of South America, they look like they fit together like puzzle pieces. That's the first piece of evidence. The second piece is that similar fossils were found in South America and Africa. So there were similar fossils found here and here, and as perhaps those fossils meant that this land was together back when some animals were living in the same area, but since that time the continents have drifted apart. They also found similar rocks in North America and Europe. So if you look here, they found similar rocks up here and similar rocks up here. Perhaps these two things were together, and since that time, it's drifted apart. And the last piece of evidence is that there were tropical fossils found in Antarctica. Antarctica is cold. Antarctica is right here. It's covered with snow and ice. How could there be tropical fossils? How could there be tropical plants living there a long time ago? Well, perhaps Antarctica wasn't always down there in the South Pole. Perhaps it was closer to the equator and has since drifted to the south. So those are the first pieces of evidence the continent is drifting. Then it was Harry Hess who thought this idea of seafloor spreading. And this came about by realizing that there was this mid-ocean ridge. During World War II, they started to develop sonar, and sonar could help them figure out how far the bottom is. And they realized there was always this ridge right in the middle of the Atlantic Ocean. And that idea, coupled with this idea that the youngest rocks they discovered were in the middle, and middle-aged rocks were in the sort of middle there, in between the middle and the edge, and the oldest rocks of the ocean floor were at the edges of the ocean, they thought, oh, perhaps that the ocean is growing from the middle and moving out, and that the sea floor, the floor of the sea, is actually spreading apart. This was this idea of sea floor spreading. And putting it all together, this idea that the continents are drifting, and that the sea floor is spreading out, came together this one idea of plate tectonics, that the crust of the Earth is actually made of these plates, and those plates are drifting around. And some of those plates have continents, so the continents drift with the plates. And some plates are made of the sea floor, but that too is moving around. This is the idea of plate tectonics, the movement of plates. This theory that the plates are moving around on this sort of pool of magma, okay? Now, what is it that drives the plates? What makes them move around? That's something that Alfred Wegener he didn't know the answer to. But we now have a better idea of what drives it, and it has to do with convection currents. It has to do with convection currents in the mantle. So first, well, what's the mantle? There are four major parts of the Earth that you'll need to know. The crust, the mantle, the outer core, and the inner core. Don't use this diagram right there. Use this one. It's a great one. This one shows the thin crust, the mantle, this is where the convection currents occur, the outer core, which is liquid, and the inner core, which is solid. And it's within the in the mantle that the convection currents move, and they act like conveyor belts to move the plates around. How did they know it was in the middle of the Earth? This was in the Bill Nye. They used seismic waves, earthquake waves, and they realized that in the middle, that the earthquake waves wouldn't always make it right through the center. There must have been something blocking the center. That's how they had this idea. There must be some sort of solid, rigid core in the center of the Earth that kind of shadows earthquake waves. And that's how they got the idea of the center of the parts of the inside of the Earth. Now they thought about convection currents. And the convection currents is when something is hot, it rises up, and it cools down, it sinks, and it goes down. And it warms up and rises, and it sinks and it cools down. And this is called the convection current. We saw that with the hot plate in the demonstration we used. And that convection current drives the plates that are on top. We use this page to sort of look at that, where these convection currents move around. If they're moving this direction, these two plates could come coming together. Right here, if magma is coming up as part of a convection current, it could be splitting the plates apart. So the convection currents are the, I think of them as like the conveyor belts that move the plates either into each other or away from each other or slides them past each other. All right, so here's another bigger picture of all the different plates. Remember that we see here where we are, an essential sort of question to help you understand the difference between continents and plates. Are we at the edge of a continent? Well, of course we are. Yes, we are. We're at the edge of the North American continent. It's right here. But are we at the edge of a plate? No, we're in the middle of the North American plate. That's why we don't have a lot of earthquakes, and we certainly don't have any volcanoes near us. Volcanoes and earthquakes, as we saw from the Ring of Fire activity, occur mostly near plate boundaries. Okay, flipping ahead a little bit here. So what are those? By the way, you don't need to worry about the lithosphere and the asthenosphere. Those are little technical terms. We don't need to worry about lithosphere or asthenosphere. So what are those plate boundaries? Well, there's three different plates. You could have one type of plate boundary where plates are coming apart. Here are the convection currents. They're moving underneath these conveyor belts and they're pulling two plates apart. When they pull the plates apart, magma can creep up in the middle and create little mini volcanoes which can create a mid-ocean ridge. There's the mid-ocean ridge. It's in the middle of the Atlantic Ocean, and as the plates move apart, they create the mid-ocean ridge. You can also have plates come together. They're called convergent plate boundaries. And there's two different types of convergent plate boundaries. One is where one can go underneath another. That's a subduction zone, right? And in a subduction zone, you can get a trench. So Japan and the Andes, that's where you can see, in fact, here's a great picture of one, where one plate subducts under another one. It creates volcanoes, it can create earthquakes, it creates a trench right there, an ocean trench. And it creates this volcanic mountains on the side. So that's an example of a convergent plate boundary in a subduction zone. That's with a continental crust and the ocean crust. You can also have one where there's ocean crust and ocean crust, but they act similar the same way. You have earthquakes, you can have volcanoes, you can have a trench, you can have tsunamis if there was an earthquake in the ocean. We'll talk more about those later. But that's another example of a subduction zone. You could also have a convergent plate boundary where two plates kind of both push up, where two continents come together. And that makes really big mountains. And this is like where India and Asia are coming together. And sure enough, they're all pushing way, way up. You get the biggest mountains when both of them push up. And that's like Mount Everest in the Himalayas as another example of a convergent plate boundary. And the last kind of plate boundary is called the transform plate boundary. And that's where they slide past each other. Now, they don't make big mountains, and they don't have lots of volcanoes, but they certainly have a lot of earthquakes because the rubbing against each other can create lots of friction and earthquakes. And a classic example of that is the San Andreas Fault in San Francisco, or in California. That's where the North American plate is going down and the Pacific plate's going up, and there's lots of friction. There can be lots of earthquakes. So here it is. The way you can remember the plate boundaries, you have divergent, convergent, transform. All right, that's it for your notes. Oh, one other quick thing though. Please also remember you should be able to practice plotting. If you have trouble with that, see me as soon as you can. But aside from that, good luck. Take care. Check with me if you have questions, and I'll see you later. Bye.